and welcome back, everyone. I am very excited to announce our next speaker, Ken Shirriff. He writes a popular blog Rido.com, on reverse engineering everything from chargers to microprocessors. He created the IO Remote library for Arduino and has written about Bitcoin mining on a 1960s punch card computer. Ken was formerly a programmer at Google and is currently restoring a Xerox Alto. Please join me in welcoming Ken to the stage.
Hi, everyone. Thank you for coming out here. So you've probably wondered, what's happening inside integrated circuits? What's inside those little packages? Maybe you've looked at die photos and thought, this makes no sense. So I'm here to introduce you to the bizarre hobby of reverse engineering old chips. So I'll start with the Z80. Any Z80 fans out there? All right, awesome. So this 8-bit CPU, here's a die photo I got from Zeptobars. Let's see if this laser pointer works. So when you look at this chip at first, you may think this is just like a crazy jumble of circuitry. What's going on here? Well, there's some ways you can figure out what's going on. These little squares around the outside, those are the pads that connect to the external pins. You'll notice that a lot of them have these green squiggly things. Those are driver transistors for the outputs. You can notice some big pads here for ground and power. And so once you've figured that out, that gives you a bunch of landmarks that you can use to look at the data sheet. And then you can label all the pins, and this gives you a huge amount of information about what the chip is doing. So you can see up at the top the control pins, so that lets you know that the circuitry up there is the control circuitry. You've got address pins around here. You follow those pins and you discover the address bus runs along here. Maybe I should move this over. I'm not sure I can see you guys over there. Data pins, you can follow them to the data bus, which runs through here. Connects to these blocks here, connects to this block up here. So already, even at this level, we can figure out a lot of what's going on in the circuit. There's a few regular blocks amid the chaos here, here, and here, and those we can look at in more detail. The first block is the register file. And whenever you see a bunch of repeating patterns like this, each one of these little blocks is one bit of storage. And so this is the Z80's internal registers. If you count down, there's 16 blocks, so it's a 16-bit register pair. So each column is a separate register. Over here, we know the address lines are connected, so we can figure that this must be the program counter and the incrementing circuit for the program counter. And then the data bus is connected over here to read out the registers. If you go into a little more detail, there's some interesting things I found. There's secret registers, WZ. These are used internally, even though they're invisible to the programmer. For internal storage. Another thing is the Z80 has a couple instructions that will swap the data in registers. And it turns out that it's actually not moving the data between registers. Instead, it swaps the control lines at the top. So it's much faster than actually moving data between registers. So just one of these optimizations that you find inside a chip. The next thing that you see in a lot of microprocessors from this era is called the PLA for instruction decoding. That's this block up here. The way this works is the data bus, we figured out, comes in here. The instruction register holds the instruction. The bits of the instruction flow back and forth across here. Each transistor will match a bit in the instruction. So what you end up with is something like, say, 001 indicates a load. That will generate a control line coming out. Other things will match all the different instructions. So this is where the matching between the instruction set and what actually happens in the chip happens. And so instruction sets get designed so that it's easy to get from a bit pattern into what's happening. The third interesting block is the ALU. This is where things actually happen in the chip, the addition, subtraction, bit operations. Most chips use a bit slice, so they'll have, for an 8-bit processor, 8 stacks of circuitry, one handling each bit of the data. Now, the bizarre thing I found in the Z80 is that you can see there's only 4 slices here. The Z80 is an 8-bit chip, but it only has 4 bits of ALU. How does that work? Well, it turns out that the performance of the Z80, the designers realized it was limited by memory speed, so they had enough time they could run everything through the ALU twice. So they saved space by putting a 4-bit ALU into an 8-bit chip. So from this level, we can figure out a lot about the chip, but to learn more, we have to dive down into the transistor level. So I'll give you the quick description of MOS transistors. For our purposes, we can consider it basically a switch. When the gate is on, it will connect the source and drain. When the gate is off, they're disconnected. On the silicon, we have a silicon layer, which is basically insulator. Parts of it get diffused with impurities such as boron to become conducting semiconductor. There's a polysilicon gate on top, separated by a small insulating layer. When the gate is on, due to semiconductor magic, it makes this part conduct. And when the gate is off, this is not conducting, and they're disconnected. A couple interesting things. This thin oxide layer is why MOS transistors are static sensitive. If you shuffle your feet across the carpet and touch the chip, the charge in the gate has nowhere to go, and it'll just blow a hole right through the oxide layer and destroy the chip. In the early days, the gate was made out of metal, so you'd have metal, oxide, and semiconductor, so that was your MOS transistor. Ever since about 1970, they've used polysilicon, so it's really a POS transistor, but they don't use that word. This is once you have the transistors, you can connect them up to form some gates. Take two transistors, you have a NAND gate. If both your inputs are 1, the gates conduct, it pulls the output to ground, and you get a 0. Pretty straightforward. And if you have a 0 input, the transistor stops conducting, and this resistor will pull the output high. And so it's very, very easy to implement a NAND gate with MOS transistors. When you look at a chip, it's a lot more complicated than that. We can zoom way in on the Z80 chip, and we get something like this. At first, it looks just bizarre, but if you stare at it long enough, it'll start to make sense. Here's what's on the chip photo, and then here's what it actually means. You can see this green region is doped silicon. We have these things that look like metal on top. That's the metal layer of the chip. That connects stuff up, provides 5 volts and ground to the gate. The inputs are polysilicon coming down. Wherever polysilicon crosses silicon, it turns into a transistor. So you see that you have your 2 transistors for the NAND gate here. And then the pull-up resistor is actually implemented with a transistor because resistors are just awful on ICs. So if you stare at these chip photos long enough and closely enough, you can figure out all the transistors, figure out the circuitry. It's a little tedious. It's easier if someone like the Visual 6502 team goes in and has people who digitize all these things into polygons, and then it's much easier to extract the transistors and the circuitry. So it's not all NAND gates, though. It's just as easy to build a NOR gate by putting the transistors in parallel. Now, if any transistor is turned on, your output is grounded. If all inputs are 0, then it gets pulled high. So that seems straightforward enough. But the designers of the Z80, they wanted to optimize things, so they made a whole bunch of crazy gates. Here's one of the gates in the ALU. It's a little hard to follow the diagram, but transistors 1, 2, and 3 connect to this yellow metal strip. Then if 4 and 5, one of those connects the metal strip to the output, so that gives you this circuitry. And then 6, 7, and 8 are transistors in series, and so that gives you a second part of the gate. So when you put this all together, you end up with a single gate on the chip is logically 5 different gates. So it makes things very efficient. These 2 gates are actually, you don't require any circuitry. They're just made by wiring the 2 parts together. So this is one of the ways they made the Z80 much more compact. I won't try to explain what this is actually doing, other than it takes ALU inputs B and C and then computes the right operation all with this one gate. So ALUs are really interesting because every chip does things differently. You might think you just take an adder, you take AND gates, and you get the logic you want, but it's all highly optimized. Because it's repeated 4 or 8 times, They try to squeeze out every bit of circuitry they can. The 6502 does things totally differently. So I've written more information on the Z80 and ALUs if you want that there. So that's the Z80. Now I'll move on to an interesting calculator, the Sinclair Scientific. The idea there was Texas Instruments made this cheap calculator chip in the 1970s. It had 320 words of instructions in it. They could barely fit 4 functions into that: addition, subtraction, multiplication, division. Sinclair took this same chip and then reprogrammed it to be a scientific calculator with logs, anti-logs, trig, inverse trig. And the mystery is, how can you take a chip that can barely multiply and make it into a scientific calculator? So I decided to find out. So thanks to John McMaster, I got this die photo of the calculator chip. You can see a lot of the same features that showed up in the Z80, the pins around the outside, ALU up here in the corner, decoding PLA, the regular register grid. It also has some things you don't see in the Z80, such as 7-segment display drivers. But the most interesting thing for us is the instruction ROM here in the middle, which holds the code that the calculator runs. If you zoom way in on it, you can actually see the individual bits on the chip in the metal layer. And so by looking at this very carefully, I was able to pull out the code that the calculator is running. Then I was also able to reverse engineer the instruction set it's using. And so I built a simulator for the calculator. So this simulator, you can try it out online if you want. It runs the exact code of the calculator. I then reverse engineered the algorithms that worked and discovered how they managed to cram all this into such a small chip. And I discovered there were 2 tricks. The first trick is that because they used scientific notation and they used RPN input, they're able to save a whole lot of code on the chip. And then they used that extra space to put in these really, really compact but really slow and inaccurate algorithms for the scientific functions. So for instance, for trig functions, they do repeated rotations by 1/1000th of a degree until you get to the angle you want. Because it's a decimal calculator, dividing by 1,000 is just a trivial shift. You do a shift and then add and subtract. You just repeat that as necessary, and you can get your sine, cosine, inverse operations. One side effect of this is that the bigger the angle you put in, the slower the calculator, because it just has to keep going until it gets to the angle. Similarly for logs, they used an algorithm with powers of 0.99 on a decimal machine. That's really easy too. You just shift 2 digits to divide by 100, and then you subtract and repeat as necessary. So that solved the mystery of how they managed to get scientific calculator out of a regular calculator. They sold a whole pile of these, even though it was super inaccurate. It's kind of sad that HP went to so much work to get their algorithms totally accurate. And in this, it's like most of the time you can probably get 3 digits of accuracy, and people bought this by the millions. Next, I'd like to move on to a forgotten bit of computer storage history. Back in 1970, RAM storage was super expensive, so Intel had something called shift register memory. This is a board from the Datapoint 2200, which some people call the first personal computer, although it says, say, the Xerox Altos first. But anyway, each one of these chips holds 512 bits, or in modern units, that's a little less than half a tweet. So it's a shift register, which means you put the bits in and then eventually they come out the other side. I cut one of these open to see what's inside, took a die photo, and here's what's inside the chip. Your bits come in, they go through these shift register stages, and eventually they come out the top here where you can read them out. At that point, you can either write a new bit or the old bit can circulate around. So if you're reading your data sequentially, this isn't too bad. But if you're doing it, you want to access something out of sequence, you have to wait until the bit you want comes all the way through, kind of like waiting for the baggage carousel. So you can wait up to half a millisecond for your data if you're unlucky. So needless to say, once RAM chips dropped in price, Intel stopped making these. We can zoom in way closer to see the actual logic. Again, we have the metal layer. We have polysilicon, and then underneath the silicon layer, on the right, I have an interpretation of it. Each bit is stored in an inverter. There's 2 clock phases. In the first clock phase, it gets passed from the first inverter to the second inverter. And in the second clock phase, it gets passed on to the next inverter. So basically, your bits just slowly flow through the chip until you get them. So now, I'd like to move on to analog chips. Anyone here ever used a 555 timer? Yeah, I figured it'd be pretty much all of you. So this is one that I cut open. Before I get into the details of that, I should talk a little bit about bipolar chips, bipolar transistors, the NPN and PNP transistors that get used. You're probably familiar with how NPN transistors, you've got a layer of N, layer of P, layer of N. The base is connected in the middle. But the thing is, when you look at ICs, it's nothing like that, just totally different. Here are some real bipolar transistors from ICs. Often you have your emitter in the middle. Sometimes it's like a right angle. Sometimes you've got 2 emitters. Sometimes you've got 6 collectors and you can't even find the base. It just gets really strange when you look inside an IC. So to explain what's going on a little more, here's a dye photo of an NPN transistor, and then here's the cross section. As you can see, it's much more complex than the MOS transistor, which is why the world has mostly moved off bipolar transistors. If you look down from the emitter, you can see the N, P, N layers are stacked vertically, but the connections are very different. To figure out what's happening in a dye photo, the emitter usually has this multiple circles. The base, you can see this faint outline here of the P layer, and then the collector is off to the side somewhere. Now you might think that a PNP transistor, you just switch everything around, but it turns out they have a totally different structure. It's more of a circle structure. Here you can see the P, the N, the P. So you do have the PNP layers, but physically the emitter is this little dot in the middle, surrounded by the base, and then the collector is off to the side, wrapping the whole thing. And then the base connection goes way underneath and comes out the other side here. It's so far away that they actually run another wire through the middle of their transistor to help the layout. So now that you know what to look at, here's a dye photo I took of the 555 timer. You can see the circular PNP transistors. You can see tiny rectangular NPN transistors, the bond wires around the outside, 3 giant transistors to provide the high current output. And then these 3 pale stripes in the middle, these are the 3 transistors that, 3 resistors that make up the voltage divider for the 555 timer that set the upper and lower oscillation limits. So you can see that resistors are kind of inconveniently large when you're building a chip. So up here we have one of the comparators. Here we have another comparator. Over here is a flip-flop. So I made an interactive chip viewer that maps everything on the chip to the schematic. You can click on something, it tells you what it does and where it is on the schematic. So you can try that out to get more details of how the chip works. Next, I wanted to talk about the 741 op-amp. This op-amp came out in the 1960s, 1968. It was hugely popular. They sold hundreds of millions of them. I'm going to explain a little about why it was so popular. Here's the dye photo I took. Again, you can pick out the transistors. There's this giant resistor, this big squiggle here, that's all one resistor. And then this big thing in the middle, that's a capacitor. And the reason the capacitor is important is that previous op-amps, you had to put an external capacitor to keep it from oscillating. Dave Fulliger, the designer of the 741, he said, engineers are lazy. If we put the capacitor inside the chip and the engineers don't have to add this extra capacitor, they'll love it. And so that's what he did, put the capacitor inside the chip, and it became hugely popular. So we can look now at more of the functional parts of the chip. The inputs go into the, we're losing a little off the top, differential amplifier there. This does the first stage of the op-amp. The gain stage provides more amplification, and then the output stage, you can see these giant transistors that provide the high current output. So another thing that made the 741 popular is this short circuit protection they added. Previous op-amps, if you shorted the output, the chip would burn up and be destroyed. They added this protection circuitry that would detect the overload and shut down the chip before it self-destructed, and this was another thing that made it very popular. So one thing that's important to understand in analog circuits inside a chip is the current mirror. Data sheets will show these symbols for a current source. And, the first time I saw a current source, I'm like, current source? Is there like a battery on this chip? Where's the current coming from? And it turns out that what it is since resistors are so awful on chips, what they'll do is they'll have a single resistor to generate, set how much current they want for the whole chip. Then they can use this circuit called a current mirror, which basically clones that current so you can get as many currents as you need just from the one resistor. And it's much more compact and much more accurate to use this current mirror circuit rather than resistors. It's kind of interesting because when you're building something on a PCB, you think of resistors as basically free and transistors are kind of expensive, but inside an integrated circuit, it's the other way around. Your transistors are pretty much free and it's your resistors that are expensive. So to see how important current mirrors are, this is the one huge resistor to control most of the currents in the 741. And then there's 4 different current mirrors that are making copies of that current. Another interesting thing is that inside ICs you find these really bizarre transistors. There's this one which has 6 collectors. This isn't something you can buy at Fry's, but it's easy to do inside an integrated circuit. The point of that was they wanted to have 6 copies of the current coming out of their current mirror, so they just make a transistor with 6 collectors, and there you go. Or if you want 2 big currents and 1 small current, you make a transistor that has 2 big collectors and 1 small collector, and there you go. So it's just some of the bizarre things you find when you look at an integrated circuit. The final chip I wanted to look at was the 7805 voltage regulator. I'm sure probably all of you have used a voltage regulator in one way, either on an Arduino or as a discrete component. So I cut this one open, and I don't know if you've ever opened a chocolate bar and you discover it's like mostly packaging and there's just this small chocolate bar inside. It's kind of the same here, just this tiny die inside this huge package. So you can see the bond wires that connect the die to the pins. The output has 2 wires for reasons I'll get to in just a moment. So I took die photos of this chip, and you can see on the right this huge transistor. This is the output transistor that provides the 1 amp output. Because it has so much current, they need to have a big transistor. One thing with the big current is you end up having some voltage drop in the wire from the output here to the output pin. So by using a second wire to sense the voltage on the output pin, they can make sure it's more accurate and account for that voltage drop. So some interesting things in this chip. Up at the top, you can see another one of these giant snaking resistors. This one provides startup current to get the chip going. You can see another big capacitor here to keep it from oscillating. These 6 transistors form a current mirror. And then over here you have a band gap regulator, which sounds really scary, but it's basically just a transistor circuit that is temperature compensated, so you can get a stable voltage even if the temperature of your chip changes. And then there's this big resistor here that's kind of interesting. Oh, that's not good. So anyway, what this resistor does is it's a voltage divider so that it can have a whole line of different chips from anywhere from like 5 volts to 28 volts with the same chip. All they have to do is change the contact between the metal layer and the resistor to change the value of the voltage divider, and that changes the output voltage. So it's just a cute trick they do so they can get a whole line of chips from one single design. So where do these photos come from? Well, I use what's called a metallurgical microscope. If you use a normal microscope, the light shines from below, which works well if you're dealing with cells, but not so good if you're dealing with something opaque like a chip. So what the metallurgical microscope does is it has this big goofy light here that shines down through the lens, so you end up with this intense light source from above, which lets you see the features of a chip really well. If you want to look at a chip, you can use a regular microscope and kind of shine a flashlight from above. And you can see a lot of it, but it works a whole lot better with the specialized microscope. You can spend tons of money on microscopes, but I got this one on eBay for a couple $100s. Once I have the microscope, I take a whole bunch of pictures of a chip, and then I tile these together using a program called Hugin. It's got a little bit of a learning curve. My first attempt, I ended up with this sort of Picasso-style cubist chip. One secret is make sure you have a way more overlap between successive images than you think you need, because that overlap is what lets it tie the photos together. So once I got that straightened out, here's a die photo I took of the, this is a Motorola interface chip. This chip was used in the Apple I, among other places. And then there's, maybe, no, I won't go into that. So now how do you get to the die? Now if you're unlucky, most chips come in epoxy, and the way to get through epoxy is you boil the chip in sulfuric and nitric acid to dissolve the epoxy. So this is what the experts like Zeptobars and Visual 6502 do. I stay away from boiling nitric acid because I don't want to end up with a Superfund site at home. So the easiest way is you let somebody else take the pictures and then you can just download them. So Zeptobars, Visual 6502, and Silicon Prawn, these are 3 sites that have hundreds of die photos. If you want to try reverse engineering a chip, you can download images from there. Most of these images, nobody has ever tried to analyze them, so just find something easy, download it, and see what you can figure out from it. Zeptobars. Zeptobars is this guy Mikhail in Russia who's done a whole bunch of chips. Visual 6502. If you haven't seen their 6502 simulator, you really need to check that out. And then this is John McMaster's site. So yeah, these are all very interesting. The way I like to deal with chips is just get chips that aren't made of epoxy, and then life is easy. So you can get analog chips in metal cans. They're cheap to get on eBay, and then you can just cut it open with a hacksaw or with a jeweler's saw and see what's inside. Other chips come with a metal lid that you can just tap with a chisel, and it will pop off, and that makes life a whole lot easier. So I've been looking at old microprocessors, and one thing I found was there aren't any good pictures of the 8008 out there. So I got an 8008 on eBay. It was all scratched up so I could get it cheap. Since it came in a ceramic package, I could just tap it with a chisel, and the top popped right off. So there's a lot of options if you don't want to deal with boiling acid. So my current project is analyzing the 8008. I took this die photo last week, so I'm just starting on the analysis. But based on what I said about the Z80, you can see a lot of similar features. You can see the pads around the outside. You can see the driver transistors, the power and ground connections. I don't know if you can see it from the back, but these regular blocks, those are internal registers. You can see the data lines running along the top to the instruction register. And then this block in the middle is the PLA that does the instruction decoding. Over here you can see 8 columns that form the 8-bit ALU. So hopefully at this point you can start to understand what's going on inside chips. I hope some of you will download or photograph some chips and start reverse engineering them, because it's a really interesting hobby and a great way to find out what's going on inside chips. So thank you very much.